This is not a place where things simply died. This is a place where things were moved. The Hilda mega bonebed sits in the Badlands of southern Alberta, a 45-minute drive north of the town of Brooks, inside a protected area called Dinosaur Provincial Park. The park is a UNESCO World Heritage Site, a landscape of coulees and hoodoos carved by meltwater at the end of the last ice age, exposing rock that is far older. The rock here belongs to the Dinosaur Park Formation, a layer cake of mudstone, sandstone, and ancient river channels deposited roughly 76 million years ago. The bonebed itself stretches for at least 2.3 square kilometers. That is the conservative estimate. Some maps place the extent closer to 3.5, and it is packed with Centrosaurus apparatus, thousands of bones, hundreds of individuals, juvenile, subadult, adult, a single species piled into the sediment like a collection of spare parts. When the site was first described in detail by David Everett, Don Brinkman, and Via Barkas, the initial reaction was predictable: a catastrophe, a flash flood that caught a herd, a drowning, a mass grave. The story wrote itself. But one bone did not fit the story. Specimen TMP 2000.12.1, a femur, left hind limb, belonging to an adult Centrosaurus. Catalogued at the Royal Tyrrell Museum of Paleontology in Drumheller, Alberta, about an hour and a half northwest of the bonebed itself. The femur is intact, structurally sound, still bearing the distinct fourth trochanter, the crest of bone where the massive retractor muscles of the tail attached. The surface should be smooth, or at least marked only by the scratches and pits of scavenging and decay. But this femur was abraded. The proximal end, the ball that once rotated inside the hip socket, was worn down, smoothed, rounded. The abrasion was not random, it was directional. It matched the pattern produced when a heavy object is dragged through fast-moving water loaded with sand and silt. If a herd of Centrosaurs drowned in a flood and their bodies settled where they died, that abrasion should not exist. There's nothing in a still water burial, in a carcass sinking in the mud, that rounds the end of a femur like river rock. The bone was telling a different story. The bone was saying, I was moved. Before you can understand what killed these dinosaurs, you have to understand what happened to their bodies after they were dead. The gap between those two events is the entire case. This is not a murder scene. It is a graveyard that moved. And the detective tool that separates those two things, the forensic science that can read the difference between death and burial, has a name. It is called taphonomy. Taphonomy comes from the Greek taphos, burial, nomos, law. The laws of burial. It is the study of everything that happens to an organism from the moment it dies to the moment it is found. Decay, scavenging, transport, breakage, weathering, compression, mineral replacement. Each of those processes leaves a mark, a signature, a piece of physical evidence, and if you know how to read that evidence, a bonebed stops being a snapshot and becomes a case file. The Hilda megabonebed was not the first Centrosaurus accumulation found in Alberta, but it was by far the largest. Earlier bonebeds from the Dinosaur Park Formation had already suggested that Centrosaurine ceratopsids, the short, frilled horn dinosaurs with the long nasal horn and the ornate spikes along the margin of the frill, moved in groups. You do not find dozens of animals from the same species buried together if they were solitary. That argument was settled. The question the Hilda site posed was different. It was not a question of social structure at the point of death. It was a question of what death meant. The site was first formally excavated in the late 1990s and early 2000s. The work was led by the Royal Tyrrell Museum, with field crews working under the prairie sun, mapping every exposed bone before it was removed. The standard protocol, photograph, sketch, assign a field number, record orientation and dip, take GPS coordinates, then jacket the fossil in plaster and burlap for transport back to the lab. Mapping is critical for taphonomic analysis because the position of a bone in the rock is a piece of evidence. A vertebra lying flat with its neural spine pointing upward means something very different from a vertebra resting on its side, angled 30 degrees from horizontal. The first tells you the bones settled in calm water. The second tells you current. When the Hilda maps were compiled, the pattern was unmistakable. The long bones, the femurs, the tibias, the humeri were not randomly oriented. They showed a preferential alignment, a statistical tendency to point in the same direction, north-northeast, parallel to what the sedimentologists had already mapped as the ancient flow direction of a late Cretaceous river system. The bones were not just aligned, they were imbricated, stacked like shingles on a roof, each bone overlapping the next, tilted in the direction of flow. That is classic fluvial fabric. That is what a flood does to objects on a riverbed. And the bones were not articulated. In a true mass death, a site where animals died and were buried in place, you expect articulated skeletons, bones in anatomical position, a skull connected to a neck, connected to a rib cage. That is what you see at a site like the Cleveland Lloyd Dinosaur Quarry in Utah, where predators and prey were trapped in a sticky mud pit. That is what you see at Ghost Ranch in New Mexico, where hundreds of coelophyses were buried in a single catastrophic flood event, many of them still intact. At Hilda, the skeletons were disassembled. Skulls separated from necks, femurs separated from hips. A few partial articulated sections were preserved, mostly the lower legs, the metatarsals and phalanges, the parts that dry out last and stay connected longest. The upper bodies, the heavy cores, were scattered. That pattern tells you the carcasses were disarticulated before they reached their final resting place. They fell apart somewhere upstream. And there is more. The bones were sorted, not by species, because there is essentially only one species here. Sorted by size. The larger, denser bones, the adult femurs and humeri, were concentrated in the lag deposits, the coarse basal layers of the flood channels. The smaller, lighter bones, the juveniles, the ribs, the vertebrae, were winnowed out, carried farther downstream, deposited in thinner lenses, or lost entirely. The bone bed is not a complete census of the herd. It is a biased sample. A filter. The flood was a taphonomic sorting machine, and it kept what it wanted, and the bones were abraded. Like the femur, specimen TMP 2000.12.1. The polish on that bone is not a laboratory artifact. It is fluvial abrasion, the result of sandblasting in a high-energy flow. Some of the bones showed percussion marks, impact fractures, from being slammed against other bones or against the riverbed. Some were broken before fossilization. The fracture surfaces weathered to the same degree as the rest of the bone, meaning the break happened close to the time of death and transport, not during excavation. Some were broken after fossilization, during compaction of the sediment. Those fractures are clean, unweathered, and filled with mineral precipitate. The timing of each break is readable. The fracture surfaces are like a clock. All of this physical evidence pointed to a single conclusion, and it was not the conclusion anyone expected when the bone bed was first discovered. The flood did not drown these animals. The flood did not kill them. The flood was the undertaker. It collected already dead bodies, already partially decayed, already disarticulated, and swept them into a channel where they were sorted, abraded, and buried under sand and silt. The death happened somewhere else. The burial happened here. That reframes everything. The question is no longer what kind of flood kills hundreds of dinosaurs at once. The question becomes, what was killing Centrosaurs in the weeks and months and years before the flood arrived? To answer that, you have to look at the bones for a different kind of signal. Not the signal of transport, the signal of time. When a bone lies exposed on the ground surface before it is buried, it weathers. Sunlight, temperature fluctuations, moisture, microbes. The organic component, the collagen, degrades. The mineral component, the hydroxyapatite, develops cracks. Those cracks deepen. The outer surface begins to flake. If exposure continues, the flaking penetrates deeper, and the bone starts to splinter along its natural grain. Eventually, the bone crumbles into non-identifiable fragments. Taphonomists have classified this process into weathering stages, from stage 0, no cracking, fresh bone, to stage 5, complete disintegration. The staging was developed by Anna Berensmeyer in the 1970s, working on modern mammal bones in Amboseli National Park in Kenya. It applies directly to the fossil record. The Hilda bones do not show a single weathering stage. Some bones are stage 0 or stage 1, minimal cracking. The surface is still smooth, only slightly checked by fine linear fractures. These bones spend very little time on the surface, maybe days, maybe weeks. Other bones are stage 2 or stage 3, deep, penetrating cracks, flakes of outer bone peeling away, the beginnings of exfoliation. These bones lay exposed for months before burial. A few are stage 4, coarsely fibrous, splintered, the outer cortex separating from the inner cancellous bone. These were on the surface for a year or more. A single catastrophe, a single event that kills a whole herd simultaneously, would produce bones in a very tight weathering range. All the animals die at the same time. All the carcasses begin decaying at the same time. All the bones begin weathering at the same time. By the time the flood arrives, the weathering stage should be consistent across the bone bed. Any variation would be minor, attributable to microenvironments, a carcass in the shade versus a carcass in the sun. Hilda bone bed shows a wide spread. The weathering stages span from nearly fresh to heavily degraded. That spread is not consistent with a single death event. It is consistent with multiple death events, separated by weeks or months, with carcasses accumulating on the landscape over time, each one beginning its own weathering clock at a different starting point. The herd did not die en masse. The herd died piecemeal, individual animals or small groups succumbing to something one after another over a period that might have stretched across an entire dry season. The flood then came through and swept the accumulation together. It gathered the fresh and the old, the newly dead and the long dead, and mixed them into a single deposit. What looks like a snapshot of one catastrophe is actually a merger of many smaller deaths into one graveyard. So the next logical step is to ask, if the flood did not kill them, what did? The fossil record at Hilda does not come with an obvious cause of death stamped onto the bones. There are no predator tooth marks that would suggest a mass attack by a large theropod. There are no pathologies consistent with a sweeping disease, though disease often leaves no skeletal trace. Death comes silently in the bone record, unless it breaks something on the way out. But we do have clues from the sediment, and clues from modern analogs. The dinosaur part formation at the time of the Hilda bone bed was a coastal plain environment on the western shore of the Western Interior Seaway, a shallow inland sea that split North America in two, from the Arctic Ocean to the Gulf of Mexico. The climate was warm-tempered to subtropical, with distinct wet and dry seasons. The rivers were large, braided, prone to seasonal flooding. The landscape was a mosaic of floodplain forests, fern prairies, and wetlands. In the dry season, water sources would have contracted. Rivers shrunk to chains of isolated pools. Vegetation thinned, animals concentrated around the remaining water. That concentration is the first ingredient in a mass die-off. Drought. A drought hypothesis works like this. A herd of Centrosaurs, several hundred strong, includes juveniles, subadults, adults, moving together across the coastal plain during the dry season. Water is scarce. The herd stays near a shrinking river or a series of water holes that are losing volume each week. The animals drink from increasingly stagnant, increasingly saline pools. The weaker individuals, the very young, the very old, the already sick, begin to drop. They die near the water's edge. Their carcasses rot under the sun. The next drought year, the same thing happens. And the next. The bones accumulate along the river margins, weathering at different rates, until a seasonal monsoon or a catastrophic channel avulsion, a river jumping its banks during a storm, scours the floodplain and sweeps the accumulation downstream. The bones are deposited in a single channel lag, sorted, abraded, and aligned. The result, a mega bone bed that looks like a single event but records multiple years of attrition. The sediment chemistry at Hilda is consistent with this story. The bone bed is hosted in a channel sandstone, a high-energy deposit that cuts into the underlying floodplain mudstones. The mudstones show evidence of Paleo-Sol development, ancient soil horizons with carbonate nodules and root traces, both indicators of seasonal drying. The environment was not a permanent swamp. It was a place that got very dry very regularly. But there is a second theory, and it comes from watching modern animals do something similar. Every year in the Serengeti, wildebeest crossed the Mara River. Thousands of animals funneling through a few crossing points. The banks are steep, the current is strong, animals panic, animals slip, animals drown. The river becomes clogged with carcasses. Those carcasses rot and disarticulate. Their bones are transported downstream, sorted by the current, deposited in gravel bars, and eventually buried in sediment that, in a few million years, could lithify into a bone bed remarkably similar to Hilda. The wildebeest are not dying of drought, they are dying of geography. The crossing kills them. Could the Hilda herd have been a seasonal migration crossing a Cretaceous river? The river in question has been mapped. The Paleo channel is wide, braided, with evidence of high discharge events. The bone bed sits inside one of those channels. The alignment of the long bones points downstream. The abrasion is consistent with transport over a few hundred meters, not kilometers, suggesting the death site was not far upstream, perhaps the crossing point itself. If a herd attempted to ford the river during a seasonal high water period, animals would be swept away. Year after year, the crossing would become a concentration point for carcasses. The flood that buried them would be the final step in a repeated process. The evidence for the crossing theory is the species composition. Centrosaurs, almost exclusively. If the bone bed were a general accumulation of everything that died on the floodplain, you would expect a mix of species. Hadrosaurs, ankylosaurs, tyrannosaurs, the other residents of the dinosaur park ecosystem, but Hilda is monospecific. One species dominates. That points to a behavioral concentration, a herd crossing a river, a herd around a waterhole, something that gathered Centrosaurus in one place repeatedly over time. The drought theory and the crossing theory are not mutually exclusive. A drought concentrates animals near a river. The river becomes the last water source. Some animals die of dehydration and malnutrition near the banks. Others, weakened, attempt to cross and drown. The two mechanisms feed the same bone bed. The flood arrives at the end of the dry season or the beginning of the wet and remixes everything. The third theory is disease. An outbreak of something infectious, sweeping through a dense herd, killing individuals over weeks. The problem with disease is evidence. Bone does not often record soft tissue infections, and viruses leave no skeletal signature unless they cause secondary conditions. There are no systematic pathologies in the Hilda sample suggestive of a widespread disease event. No lesions, no feature osteosis, no abnormal bone growth. The absence of evidence is not evidence of absence, but in this case, the physical evidence for drought and river concentration is stronger. The disease theory remains the third suspect on the board, with the least supporting evidence. What you are left with, after 12 years of excavation and analysis, is this. A herd of Centrosaurus apparatus lived on the coastal plain of what is now southern Alberta. The herd included multiple age classes, a natural population structure. These animals were gregarious. They lived together. They moved together. The age profile from the bone bed, with juveniles making up roughly 20% of the sample, subadults 30%, adults the remaining 50%, matches what you would expect from a living herd, not a random accumulation. There is some bias. Juveniles are underrepresented, probably because their smaller, more fragile bones were winnowed away by the flood. But the signal of herding is robust. This is one of the strongest pieces of physical evidence for social behavior in Centrosaurian ceratopsids. The herd died, not all at once, in pieces, over months, over years. The cause was likely environmental stress, drought, and the hazards of a river crossing. Their carcasses accumulated along the river system, weathering at different rates, scattered along the bank and the channel margins. Then a flood event, a seasonal monsoon or a channel of ocean, scoured the accumulation. The water picked up the bones, already disarticulated, already weathered, and transported them a few hundred meters downstream. The current sorted them by size and density. The heavier bones settled into the channel lag, aligned with the flow, stacked shingle style. The lighter material was carried away. Sand and silt buried what remained. Over millions of years, the sediment compacted, lithified, the bones mineralized, the rock was lifted by tectonic forces, and the top layers were stripped away by Pleistocene glaciation and Holocene erosion, until the bone bed sat exposed in a badland coulee, waiting to be mapped. Specimen TMP 2000.12.1. The femur is both a witness and a victim. Its abrasion tells you it traveled in fast water. Its weathering stage, a stage 2, with deep checking and early flaking, tells you it lay on the surface for at least 2 months before the flood arrived. Those two facts connect the two events. The death happened during a dry period. The burial happened during a flood. The bone passed from one world to the other. This is the central lesson of forensic taphonomy. A bone bed is not a photograph of an event. It is not a snapshot. It is a composite, a palimpsest. A palimpsest. A document that has been written over, erased, and written over again. The original signal, the cause of death, is overprinted by the processes of decay, weathering, transport, and burial. If you do not strip away those later overprints, you will read the wrong story. You will mistake the flood for the killer. The Hilda mega bone bed is a graveyard. But the real crime scene, the place where these animals actually died, is somewhere else upstream. Somewhere still buried, or eroded away entirely, or hidden under a few meters of overlying rock, waiting for the next field season. The case is not fully closed. It never is in paleontology. Each new excavation, each new analytical technique can reopen the file. Stable isotope analysis of the enamel on Centrosaurs teeth might tell us the exact season of death. Histological sampling of the femur. The same specimen, TMP 2000.12.1, might reveal lines of arrested growth, stress markers that correspond to seasonal hardship. Micro-CT scanning of the internal structure could show microfractures from trampling or transport. The tools get sharper every decade, but the verdict, for now, is this. The dinosaurs at Hilda were not killed by a single disaster. They were not drowned by the flood that buried them. They died slowly, in pieces, across a landscape that was drying out around them. The flood was the collector, not the executioner. It gathered the dead, sorted them, abraded them, and sealed them under sand. It created a graveyard that looked like a crime scene. The bones are witnesses. They do not remember the moment of death. They remember everything that happened between death and discovery. The job of the taphonomist is to listen to that memory, to separate the signal of the original event from the noise of the burial process, to ask the question that any good detective asks when walking into a room full of evidence: what happened here before they put the tape up? In this case, the answer is not a single moment of violence. It is a long, slow accumulation of loss. A dying season, a river that offered water and then swept the bones away. A herd that moved across the landscape for years after its members had already started to become part of the rock. The graveyard is not a place where they died. It is a place where they ended up. And the femur, specimen TMP 2000.12.1, still sits in the collections of the Royal Tyrrell Museum, a piece of physical evidence in a 76-million-year-old cold case that, against all odds, gave up its secrets to anyone willing to look closely enough. The bone does not lie. The bone cannot. It simply has to be read. The case of the Hilda mega bone bed is, for now, resolved. The next bone bed is waiting.